Back in Year 8 we talked about acidity as being measured by a scale called a pH scale, and the scale went from 1 to 14. If you have a look at the diagram on the right, you'll see some common substances and the pHs that we measured. You'll remember measuring the pH of lemon juice as having a pH of 2, oven cleaner as having a very high pH. So that things that were very acidic had low pHs, things that were quite basic like ammonia had fairly high pHs, and distilled water had a pH of 7, which was the neutral pH, where something is neither acidic nor basic. This diagram shows the relationship between the hydrogen ion concentration and the pH. Can you see a pattern that occurs here? If we have a pH of 2, that equates to 0.01. If we have a pH of 10, we have 9 zeros and then a 1. Now, it would be tempting to think that the number of places after the decimal point gives us our pH. In many cases that's possible, but it's not quite as simple as that. If you look at this table, which shows the hydrogen ion concentration and the pH, in the first instance we have a hydrogen ion concentration of 10 to the minus 1 and a pH of 1. And for a concentration of 10 to the minus 2, the pH is 2. So it looks as if the pH is going to be the number that the 10 is raised to the power of. It becomes a little bit more complicated when you get concentrations given to you like the third one, which is 0.0025, and the pH comes out as 2.6. And similarly in the last one, where we have 4.57 by 10 to the minus 9, the pH is 8.34. So it's not exactly the number that the 10 is raised to the power of. We have to turn that number in front, the 4.57, into a negative log to be able to do our concentration. So the actual relationship between the pH and the concentration is that the pH is equal to the negative log to the base 10 of the hydrogen ion concentration. Since it's a negative log, that means that as our concentration gets higher, then the pH will get lower. This also means that if we change the hydrogen ion concentration by a factor of 10, because we have a logarithmic scale, the pH is only going to change by 1. So if we have a hydrogen ion concentration of 10 to the minus 2 with a pH of 2, if we take a dilution of that and take only a tenth as much, the pH is actually going to increase by a factor of only 1, and so we'll have a pH of 3. Similarly speaking, if we change the pH from a pH of 4 to a pH of 6, looking at our concentration, the pH of 4 is 10 to the minus 4, pH of 6 is 10 to the minus 6, so the actual concentration of the solution is 1/100th of the concentration of the pH 4 solution. So how do we actually go about calculating a pH? First of all, we need to work out whether we've got an acid or a base. And once we've worked out that we need to work out what the concentration of hydrogen ion or hydroxide ion is. This will depend on whether we've got 1, 2 or 3 hydrogen ions being released, which in the case of a monoprotic acid we'd have 1, a diprotic acid we'd have 2. Similarly speaking with a hydroxide ion, if we've got sodium hydroxide we'd only have 1 hydroxide being released, but if we've got calcium hydroxide we'd have 2. Once we have that concentration, if we've got H3O+, we can just calculate the pH directly by taking negative log of the hydrogen ion concentration. But if we have to get the pH when we've got a hydroxide situation, we can first of all have to calculate the H3O+ using our ionic product and then turn it into a pH. So in this particular case, we want to calculate the pH and the pOH. pH obviously is going to refer to the hydrogen ion concentration, and the pOH will refer to the hydroxide concentration. So if our solution has a concentration of 0.0135, just by substituting our figures into the pH equation, we can come up with a pH of 1.87. Now, if you think about it, that's less than 7, so it's acidic, which is what we expect it to be. But what about getting the pOH? All we need to do for that is subtract it from 14. 14 minus the 1.87 gives us a pOH of 11. That means that the hydroxide ion concentration is 10 to the minus 11, which makes sense in the context of this question. Something you might need to think about is actually using your calculators to do this. If you have a scientific calculator, If you press minus log and then put in the concentration, that will give you the pH. Likewise, if you want the hydrogen ion concentration, then you press the 10 and the YX button and then type in the negative pH value, and that should give you your answer. If we want to do the reverse procedure and calculate the concentration from the pH, you remember that the hydrogen ion concentration is equal to 10 to the minus pH. So if we have a pH of 3.5, then our hydrogen ion concentration is 10 to the minus 3.5. And if you substitute that into your calculator, you should get 0.032 molar as your hydrogen ion concentration. Now, if we wanted to get the hydroxide concentration in that solution, we can do that by subtracting that pH of 3.5 from 14 and then turning it into a concentration, because you remember that the ionic product tells us that the H3O plus times the OH minus is always going to be equal to 10 to the minus 14. So in this case, if our pH is 3.5, then the POH will just be 10.5, and therefore the hydroxide concentration will be equal to 10 to the minus 10.5. We can convert that into a concentration. Now what happens if we've got a solution which isn't actually an acid and we're asked for the pH? So for instance, if we've got 0.01 molar sodium hydroxide, then we know the first step that we have to do is to work out what happens to it in solution. And in this case, it dissociates to give us hydroxide ions. Because it's a strong base, then the concentration of those hydroxide ions is going to be equal to the concentration of the sodium hydroxide, in other words, 0.01 molar. The third step is then to turn that into a POH by taking minus the log of the hydroxide concentration, which in this case will be 2. And then because we know that the POH plus the pH is equal to 14, by subtraction we can get that the pH of this solution is going to be 12, which is what you would expect because it's a strong base. This problem is starting to get a little bit more complicated. Here again we've got a strong base which is going to dissociate in solution, but we've got 2 hydroxides within the compound. So if we want to find our pH, we need to know the H3O plus concentration. When we put barium hydroxide into water, it breaks up to give us barium ions and 2 hydroxide ions. So if we're going to calculate our concentration of hydroxide, we must remember that we get 2 OHs for every barium hydroxide. So our first step was to calculate the concentration of hydroxide ions. Hydroxide ions in this case will be twice the concentration of the barium hydroxide, which is twice that 0.005, which is 0.01. The second step in the procedure was to use our ionic product to turn that into a concentration of H3O plus. So if we substitute in our 0.01 and do our division through, then we come out with a hydrogen ion concentration of 10 to the minus 12. And again, think logically, that makes sense because we're actually in a basic solution, so it should be about 10 to the minus 12. Then we need to turn that into a pH by taking minus log to the base 10. 10 minus 10 to the minus 12 is going to be equal to 12. What happens to the pH in this solution? First thing we have to do is recognise what type of problem this is. We've got an acid where we're given the concentration and the volume and we're adding water to it. So it's obviously going to be a dilution problem. So our tendency would be to think that we can use C1V1 equals C2V2. So let's see what we've got. We've got 30 mils, which is 0.03 litres. We've got 50 mils of this one, which is going to be 0.05 litres, and we've got a concentration. So what we're missing is the concentration after we mix the two together. 1 molecule of nitric acid gives us 1 hydrogen ion, so therefore the concentration of that hydrogen ion is going to be equal to the concentration of the nitric acid. So we don't have to worry about diprotic or triprotic acids. So the first thing that we have to do is use our C1V1 and substitute in our figures. So our first concentration is 0.1, our volume is 0.03, and our second volume is 0.08 because we have to add the volume of the nitric acid to the volume of water, so that's the 30 plus the 50. Solving for C2, we then get that C2 is 0.0375. So that's the concentration of our hydrogen ion in that solution. Then we need to turn that into a pH. pH is just minus log to the base 10 of our concentration, which we've calculated, and substituting that in, it gives us a pH of 1.43. Now you can do a quick check in your head and look at that. The pH of the solution to begin with would have been a pH of 1. We've diluted it down by adding water, so therefore the pH should increase, which is exactly what's happened. Let's have a look at another type of problem. In this case, we've got nitric acid being mixed together with hydrochloric acid, and we want to find the pH of the mixed solution. Now remember, we've got two different substances being mixed together here. We're not just adding water. Both of them are monoprotic acids, so they're both going to contribute to the pH. So that means we're going to have to find out how many hydrogen ions are coming from each one. So the first step we have to do is to calculate our total number of moles of H3O+. And we can do this just by using our formula N equals CV. So the nitric acid has to be calculated separately from the hydrochloric acid. By substituting in our values, we get 0.01 moles for each one of them. And if we're adding them together, we just get 0.02. So that's our total moles of H3O+, because each one of those acids is going to give us 1 unit of H3O+. So now we know our total moles, we need to work out our total volume to get our overall concentration. So our total volume is just found by adding together the two volumes of 50 mils and 20 mils, which gives us 0.07 in litres. And then we can calculate our hydrogen ion concentration, just again using the formula concentration equals the number of moles divided by volume. So in this case, we've got 0.02 moles as our total moles of H3O+. We divide it by our total volume to get a concentration of hydrogen ions of being 0.028 molar. And if we substitute that into our pH calculation, we get that the pH is just 0.55, which means it's a fairly strong acidic solution.